Upward to the cloud. Okay. All right. So today we're talking about the general method of characteristics. Okay. And said in brief, this is a way of converting a quasi-linear PDE to a set of ODEs that tell us about the evolution of solutions along these curves, basically these parametrized curves along the solution surface. And if we recall from last time, the general PDE that we had was this function a of x, y, and u times u sub x plus this function b of x, y, and u times u sub y equals potentially some nonlinear function c of x and y, okay? And the way that we want to think about solving this is that we have some initial data, okay, or you could call it boundary data. For our transport equations on the quadrant, this would be like, you know, both the x boundary and the t boundary, just some boundary from which the solutions will emanate. Sometimes you're just going to have an initial condition just along x in the real numbers from 0 to infinity. And along this, you have a parameter s that determines how you move along this initial data, which is given by, we called it capital gamma. And then as you move off of this, you'll move forward in some parameter tau that's going to parameterize how far you are along a characteristic. And what determines the movement along this is these coefficients a, b, and c. And the normal to this is going to be ux, uy minus 1. So that a, b, c dotted with the gradient of u minus z. You know, z is our whole solution surface. Okay, z is equal to u of x, y. Okay, this is going to be equal to just our left-hand operator, and then we shift over that function from the right-hand side c. We say that's equal to 0. Okay. So the idea is that we're parameterizing the solution surface with these parameters s and tau. So these are like our new variables rather than x and y. And so x is now, we think of as equal to some function of s and tau, y is equal to some function of s and tau, and z is equal to some function of s and tau. And if you remember from the general transport equation that we found, when we parameterized x in the right way, we could take a total derivative and get back the operator that lived on the left-hand side of our PDE. The idea now is that if we write u as x of s tau and y of s tau, okay, and we write z as a function of s and tau, then d tau of u of x s tau y of s tau minus this z of S tau. What's that going to be equal to? Well, just applying the chain rule, essentially we'll have dx d tau u sub x plus dy d tau u sub y minus dz d tau. Okay. So what does this tell us? Well, if we look back up here, it tells us exactly what the ODEs are that we should write for x and y and z, right? Dx d tau should equal a, dy d tau should equal b, and dz d tau should equal c, okay? So now that we've done this sort of general work up front, we can just take the method of characteristics and read off the ODEs that we need to use each time, okay? So this tells us then that there's, I'll go through the 3 steps of method of characteristics, okay? The first is to generate a solution surface, okay, from the integral curves of these ODEs, okay? So what's involved in this? Essentially, we're just going to write and solve the following ODEs, okay? So what are we going to probably need for this? We're probably going to need to recall some methods from differential equations for solving potentially nonlinear differential equations. You know, separation of variables. We may, come across some systems of differential equations. We may occasionally encounter some that, all we can do is kind of look at phase planes or something like that, okay? And so writing now, replacing u with z, right? So essentially, we'll replace u with z because we know that z is just equal to u. We have that dx d tau is equal to x, a of x, y, and z, okay? With some initial condition, x0 is equal to x0 along the parametrized curve, okay? And if I just have if I just have the x-axis as my initial condition, then we can just take x is equal to s. If it's some more complicated, curve in space, we may need some different parameterized curve, but this should be good enough. So we'll see how this plays out in examples. It'll become a little less mysterious, I think, when we go through an example. Okay. The other 2 ODEs are dy d tau is equal to b of x, y, and z. Okay. And again, we need an initial condition, which is that y of 0 equals y0 of s. And finally, we have dz d tau is equal to c of x, y, and z. And z of 0 is equal to z0 of s, okay? And this mapping from the initial data to these initial conditions is not necessarily unique. You can pick different ways of doing this, okay? But typically you want to do something like, well, if it's just an initial value problem and, y is actually like time, you probably want to take, y0 is going to be equal to 0 because that would just be your initial time as t equals 0. x0 would be s. And then z0 would just be your initial condition of s instead of x, okay? So a lot of the examples that we'll come across, that's kind of good enough for handling this initial data. And then you just sort of read off what these right-hand sides are from your original PD, okay? That's the first big step, is setting up the ODEs, okay? And then you have to solve them, okay? And in general, I can't tell you, how you would solve every single one. But essentially, you're going to have some solution that's going to be given x, y, z of s and tau, okay? And these are going to be your characteristic curves, okay? When I fix a particular value of s, that's going to be one of my characteristic curves, right? So these are going to be, this would be one particular characteristic curve, okay, given by x, y, z of s tau. This is my sort of s-axis here, and this is the flow of tau forward, sort of tracing out this characteristic curve, okay? And these characteristics, they project the solution to the xy plane, okay? So the point is that I have a solution that's parameterized by s and tau. At the end of the day, I don't really want this solution in terms of s and tau. So what I have to do is invert this expression to get z just in terms of x and y instead of s and tau, okay? So the second step then is to use the inverse function theorem, okay? That's what came up in that very first example that we looked at on Monday. So in this case, we know the curves are parameterized by s and tau, right? Okay. To get back to xy, okay, we need to invert the mapping of s and tau into x and y, okay? And this will yield some function u of xy. Because remember, we have z in terms of s and tau. If we can get s and tau in terms of x and y, then we'll just have some function of x and y and we're done, okay? But how do we know that we can actually employ the inverse function theorem, okay? We need to check a particular condition. And that specifically is the Jacobian, okay, that determine of the functions that determine the mapping from x and y to s and tau and vice versa, is that invertible, okay? So what's a Jacobian? It's just, for this particular case, it's going to be the derivative of x with respect to s, the derivative of x with respect to tau, the derivative of y with respect to s, and the derivative of y with respect to tau. Okay, just like the Jacobians you work out for phase plane analysis. So is this invertible? Okay, and so you can just plug in what you have for x and y, compute that, see if its determinant is non-zero or not, okay? And if you want to know more about how you get from the inverse function theorem to this condition, okay, you can read theorem A1 and A2, okay, in the book, okay, which is in the appendix. All right.
Do we have to have this at a specific point, like S and T, like initially, or does this have to be true for all S and T?
Yeah, it has to be true basically at your initial data. So you can compute this Jacobian's determinant, and you check it at the initial data to make sure it's invertible at the initial condition. And then just like that example that we talked about yesterday, yeah, that's a good point. This ensures that you'll have a solution in some neighborhood of the initial condition. Really, the way to check that it works is then to construct the solution and to see that it, continues to be valid in the whole region that you're looking at. But yeah, you could have that it satisfied initially, but then it breaks down later. But for our purposes, in order to solve with method of characteristics, you check it at the initial data. Yeah. Okay, so if you check this and it works out, okay, then the inverses S of xy and T of xy should be substituted into U equals Z of S of xy and tau of xy. Okay, so then you get, a function of x and y. Okay, so finally, we can write our solution surface. Okay, and that's just going to be this Z equals U of xy. Okay, and as mentioned, we need this following condition, right? That the determinant of the Jacobian needs to be non-zero. Okay, so in our case, this is given by x0 prime of s, y0 prime of s, and then these two terms here are just given by your right-hand side at the initial data. A of x0 of s, y0 of s, and z0 of s, b of x0 of s, y0 of s, z0 of s. We want this to not be equal to 0, okay? So basically along our initial data, okay? And this means that A and B are not going to be tangent to our initial data, so we can basically step off of this. If this was non-invertible at some point, it would mean that we can't do this thing up here. We can't go from the initial data to a characteristic that flows away from it. It would mean that the flow is right along our characteristic. So we're going to have issues with degeneracy. We're going to have issues with actually being able to have our characteristics move off of the initial data. So that's why we have to check that condition. And that's what allows us to sort of, invert things and get this solution, okay? So, so let me just make that remark. So we check invertibility along initial curve so that A and B are not tangent to gamma, that initial data, okay? And the result at the end of the day is that we have a unique C1 solution, U of xy, for xy near the initial data. Okay. All right. That's what this method promises us. Okay. So questions about that? This is sort of the end of the first part of this lecture. Okay. I think more yeah, go ahead.
This is minor, but when we took on the previous page,
Yeah.
At the bottom there where we took the Jacobian xy with respect to s tau, why didn't tau show up at all when you expanded it out with x not a prime of s and a all of s?
Yeah, so that's because along the initial data, we have that the only yeah, that's right. The only, we're assuming basically, yeah, so I'm sort of sweeping some things under the rug here, right? This is saying, you know, x of s0 is equal to x0 of s. This is saying that y of s0 is equal to y0 of s. So along the initial curve, you're assuming that tau equals 0. So I've just dropped the tau equals 0 argument there. But if you like, yeah, this should involve this thing here should be x of s0. But x of s0 is just equal to this function x sub 0 of s. So I sort of took, you know, you're just taking the, you know, tau equals 0 and putting it in as a subscript here.
Okay, thank you.
Yeah. It's just a little notational thing. Yeah. Okay.